So, hi everyone, I'm Rohit Kumar Singh, and this is the sixth live session for this course, Wave Optics. Uh, Today we will recap the concept of diffraction, and we'll solve some examples based on these concepts. Okay, uh, so let's start. Do you have any question or anything to ask before I begin? Okay, if not, then we can start. Sorry. Are you able to read, or the marker size is small? Is it fine, the marker size? No, you're not audible, Priyank. Oh, sorry. I think I have. Okay. Now can you speak?
Yeah, sir, I was saying today we were going to study Fabry Perot, that one
Yeah. So yeah,
interferometer.
yeah. I told you that we will study Fabry Perot, but so what I saw is that the diffraction itself has many topics this week, and if I cover Fabry Perot, then we'll again left behind. So what I plan to do is keeping Fabry Perot as a special topic that I can discuss in an extra session. So there will be an extra session at the end, so we can discuss that there. So yeah, I have that in mind. Is that okay?
Yeah, yeah, yes, sir. We can whatever happens. Yeah.
Okay. So okay, then let's study diffraction today. So so far we have been studying this wave optics, and we were studying for from 3 weeks the interference, what is interference, and what are the criteria for interference and things like that. Different methods to get interference, and we saw many uh, mm, different experiments uh, where interference happens, and we can measure the wavelength of light and many various things, right? Now there is another phenomena related to wave optics, which is diffraction. So what is diffraction basically? So I mean, from a physical point of view, diffraction and interference are not so different. Okay, are different. They are basically the same phenomena, and it is just a convention to study them separately. So, but from physical point of view, it is the same phenomena. Okay, both are due to the wave nature of light, and both happens when a light of particular wavelength passes through slit uh, having the size similar to the wavelength of the light. So it's not I mean, both are not very different from each other. Okay, so let's keep that in mind. Now what is basically diffraction is, so if you have a opening like this, so uh, and its width is like given by b, okay, and you have light rays coming, parallel light rays coming like this, and there is a screen here, okay. So what you expect to observe is that, I mean, in daily life, what you will expect is that there will be a you know light here, and then so this part will be illuminated, and the rest will have shadows, right? These part and this part will be dark. That's what we expect, right? But if this slit width is of the order of the wavelength of the light, that is the incoming light, then something interesting happens, and you get illumination in these portions also, okay, where you expected it to be dark. And this phenomena is what we called diffraction. So in ordinary day-to-day life, you don't observe this, because you know that the wavelength of the visible light is of the order of 500 nanometer, around, like, okay, 400 500 nanometers, and this is a very short distance, right? So you don't have our eyes are not tuned to observe uh, you know this kind of distances. But it happens, like, in a laboratory we can see this, we can measure this, okay. So yeah, so this is what basically diffraction means. Now there are two types of diffraction, okay. One is Fresnel diffraction. So these are two different classes of diffraction. So here the screen where we observe the diffraction pattern, or the this source, they are at finite distances. Finite distances to what? To the uh, diffracting aperture or slit, okay. And the another class is, so it will be like this. So this is the slit, you have the source here, okay. Source, the light rays goes like this, and you have the screen here, okay. So okay, so something like this we call Fresnel diffraction. So all these distances are finite. So finite distances means the light rays that are coming at the slit are not parallel, okay. So for that, you what we call another class of diffraction called Fraunhofer diffraction. Now here both these distances are infinite. Now what does infinite mean? Like, we cannot keep in our laboratory we cannot have infinite distances, right? Infinite means the light rays should be parallel, okay. The light rays arriving at the slit should be parallel. Now how to make it parallel? So to make it parallel, you can simply take a convex lens, right, and keep it before the slit. So even if the source is at at a finite distance, uh, the light ray after the convex lens will be parallel, okay. Similarly, before the source you can keep a convex lens like that, and it will, so parallel light rays will go here, and then it will converge to some point like this, okay. So and this distance should be the focal point, focal length of the lenses, okay. Is that fine? Okay. Yeah, so this is these are two different categories of diffraction. Now this Fraunhofer is easy to study and understand, because you have parallel light rays. So the equations, the everything, all the calculations become easier. So for now we will focus on only the Fraunhofer diffraction, okay, where we'll assume that the light rays coming on the slit are parallel, okay. So okay, so let's do some calculation. So quantitatively we will see uh, how the diffraction happens. Okay, so let's first focus on a single slit diffraction. So single slit diffraction means there is only one slit like this. Okay, so let me draw it. uh, so let me draw a schematic diagram. So it will be, so slit is basically this one is your slit. Okay, and this width is your slit width. Okay, this one is considered to be very long, like this should be greater than b. Wait. So if this distance we call it, you can call it anything like what do we call it? So suppose d should be greater than b. Okay, it's basically we call it infinite. And so what will happen is light will enter this slit, goes out, you have the lens. Okay, and the diffraction pattern, so this is the screen. Okay, now in which direction should you get the diffraction pattern? Like this or like this? Any intuition?
Along the length of the slit.
Along the length of the slit. So you're saying this?
Yes, sir.
No. So that's what I said. Slit width is b here. Okay, slit width is so not the not the vertical one, it is the horizontal
Yeah,
one.
I understand now, yes, sir.
So this, in this direction you will get the diffraction pattern. Okay, so we'll see how it happens. So now let me draw a schematic diagram from where we can derive the condition for diffraction, minima, maxima, and so on. So this is let's say this is the slit. Now let's call this point A1. Okay, and so yeah, this whole distance is now b. Okay, so you see from this figure, uh, this x, so suppose if this is your x axis, sorry, so suppose this is your y axis, so the y axis here is coming out of the plane. Okay, and so here this is the x axis, so basically I have drawn here the x axis. Okay, so this is the x axis and the y axis is actually coming out of the plane. Okay, are you able to understand? Yeah, so we are not concerned about the y axis. The slit that we are concerned about is in the x direction. And this is illuminated by parallel rays like this. So suppose this point is A1. Okay, and now do you guys know the sorry, Huygens principle.
Yes, sir.
Sorry, what is the spelling? I forgot. Uh,
Huygen.
HUI. Okay, yeah, yeah, yeah. Thank you. So yeah, I am keep writing Y. HUYGEN. Yes. Yeah. So Huygens principle tells. So yeah, tell me what is Huygens principle?
Sir, it tells like the wavefronts are there,
Yeah,
which
yeah.
are
Hmm.
perpendicular to the rays of light.
Yeah.
There are many kind of wavefronts, sir. Spherical wavefront, plane wavefront, like that.
Yeah, yeah. No, no. Yeah.
I like,
Wavefront
yes,
idea is fine, but what Huygens principle also tells is that at each point of a wavefront, okay, you get a secondary. You have a secondary wavelet emanating
yeah,
like this, right? So each point of wavefront can be considered as a source of a secondary wavefront, right? Yeah. So no. So that's the idea that we are going to use here. So suppose there is a point A2 here, okay? Now, yeah. So suppose this parallel rays that are going falling here, they have a wave front, okay? They will have a plane perpendicular, yeah, plane parallel wave front, and that wave front can be considered. So at A1 we can consider secondary wave fronts coming out. At A2 we can consider another secondary wave front coming out, okay? And these two uh, can interfere with each other, right? Because they are from the same, they are part of the same wavefront. uh, so and they are in phase, right? They have the same phase relationship, so they can interfere with each other, given that there is some path length difference, some phase difference. Now how the phase difference can come here? So if you look at, so suppose, since we are talking about Fraunhofer diffraction, we have a convex lens here and a screen here. So suppose from A you have this path of light ray is going like this, okay? And at A2 it can also go like this, okay? So these two wavelet will have a path difference, let's call it A2 prime, given by this distance A2 prime, right? This is the path difference between these two. So this convex lens will now converge it to the same point, and similarly there will be a different point A3 here, from here also. So let's call it P, okay? So wavelets from A1 and A2 will have a path length difference of A2 prime, right? And let me write it. A1 A2, the distance A1 A2 is basically, let's call it delta, okay, small distance. And A2 prime will be what? It will be so if this is a angle theta, okay, then it is just delta sine theta, right? Also, since these small distances are delta, this total slit width will be b is equal to n minus 1 delta, where n is the number of divisions that we are making. Why not n delta? Why is this n minus 1 is there?
Sir, I did not understand this part.
Sorry,
Can you say this again?
yeah, which part? Like this one, this equation?
B, yeah, yes, sir.
Okay, yeah. So I'm saying that this, so we have this slit, okay, and we are making divisions. So from A1 to A2, A2 to A3, and so on, okay. And all those divisions are have this distance delta. So b is equal to what? B should be equal to n delta if you are making n divisions.
Yes, sir.
But why it is n minus 1 delta? That's what I'm asking.
If the divisions are n, so B should be equal to n delta.
Yeah,
That is okay.
but it depends on like so no. But see, let's take the case up to A3. Okay, so A1 A2 is delta, and then A2 A3 is delta. Okay, so we have made 3 divisions, right? N equal to 3, but you have just 2 deltas, right?
Yeah, yes, sir, I understand now.
Yeah,
Okay.
so that's why
That's why.
it is not n delta but n minus 1 delta. Okay. Yeah, it's a little tricky. So, okay. Oops. Okay. Yeah. Okay. Till now it's fine, right? So now this is the path difference from A1 and A2. Okay. And corresponding phase difference given by phi will be just 2 pi by lambda times this path difference delta sine theta. Fine.
Yes, sir.
So we are just now concerned with only 2 points, A1 and A2. Okay, we will see later what happens. Okay, so these 2 points, so they have no path difference and they will interfere, right? So now you see the diffraction is nothing but just a manifestation of interference. Okay, interference between the same wavefront, among the same wavefront. Okay. So what will happen at P, at point P, where we have put the screen? Okay, so we can write in terms of amplitude. So we have studied this. So light wave are given by electric field amplitudes. I mean, basically these are electric field, and so resultant electric field at P due to these two wavefront. So let's assume the amplitude to be A, and this is the cos omega t. So only time variation, and the other one will be shifted by a phase phi. Correct? This will happen for the 2 points. Now if you have similarly n divisions like this, then you will have to add all those. So cost, no, the third one, the A3 will be shifted by how much distance? Two delta sine theta, right? It's just twice. So similarly, you will have this cos omega t minus 2 phi and so on, and the last term will be cos omega t minus not n phi but n minus 1 phi. Again with the same logic you can see. Okay, because the last one is n minus 1 delta, so it is n minus 1 phi. Now you have so to get the resultant amplitude you'll have to sum all these. Okay, so there is a standard summing formula for this. I think you can look at any standard textbook, and so this in the bracket what you have, if you sum this series together, you will get this value. Okay, so it is it is basically, you can simply see that this is just cos A cos plus cos B. Okay, then you get a get something, then you sum cos C cos D and so on. Okay, so you know the this formula, right? cos C, cos A plus cos B is equal to what? 2 cos
2 cos A plus B
Yeah.
divided by
A plus
cos
B by 2
A minus B by
and
2.
cos A minus B by 2. So using this, I think one can derive this. So you can check any standard trigonometry book, it should be there. So okay, so this is the resultant amplitude of the electric field. Okay, and let's call this first term. So this first term, you notice this sine term, it has no time dependence. Okay, so it is like the the resultant amplitude the resultant amplitude of the resultant electric field. Okay, so let's call it E naught, and what you have in cos is omega t minus half n minus 1 phi. So this is the resultant electric field due to all the different wavelets coming from the same wavefront. Now it's up to you to to keep this delta distance as much as small you want. So we will see when n goes to infinity and delta goes to 0, what happens. Okay, that we will see here. Okay, so this is the resultant electric field. So if now we make infinite divisions of the slit, okay, so n goes to infinity, and this delta v, the distance between the divisions, they become smaller and smaller, and then they tend to 0. Then in that limit, in that limit, b, the slit width is nothing but n delta. Okay, so earlier b was what? N minus 1 delta, right? But since now n is infinity, so 1 doesn't matter here. Okay, so b becomes just n delta in this limit. Okay, and now in this case what happens is n phi by 2, which is equal to so phi we wrote here, phi is 2 pi by lambda delta sine theta, right? So let's write it here, n pi by lambda delta sine theta. 2 gets cancelled from numerator denominator. Okay, so what happens when so n delta you have here, so it becomes b. So you have pi by lambda b sine theta. Okay. And so yeah, and so now phi from here, phi will be what? 2 pi by lambda b sine theta by n. It goes to 0. Right? Yeah. So if this happens, then the amplitude that we calculated, which was a sine n phi by 2 divided by sine phi by 2, right? It becomes, so since phi goes to 0, right, phi tends to 0, in that limit it is just yeah, a n phi by 2 divided by, no, wait, sorry, n is there inside, so you cannot take it out because n is infinity here, right? So n is infinity but phi goes to 0, so it still remains like you cannot put it to like you cannot take it out. So let's keep that as it is, and this denominator sine phi by 2, so here the phi goes to 0, so in the limit phi goes to 0, sine phi by 2 is equal to phi by 2. You know that, right? That sine x is equal to x limit x tends to 0.
Yes, sir.
Yeah. Okay. So then finally you can write the phi from here. I mean, substitute phi, this phi here, and you get E naught equal to so this is phi, and here you have pi b sine theta by lambda. Okay, n goes here, and this we can write concisely as a sine beta by beta. Okay, where a is equal to na and beta is equal to pi b sine theta by lambda. Okay, let's keep it equation 1, we will use it later. So now what happens is your resultant electric field can be written as sine beta by beta cos omega t minus beta. Okay, is that fine? So this is when we have let n goes to infinity. In that limit we can write it like this. And now what is the intensity? So we know that intensity is just the amplitude square. So this is intensity is sine square beta by beta square. Okay, and I naught is the intensity, at basically theta equal to 0. So this is the maximum intensity. Okay, that is when beta equal to 0, sine beta by beta is equal to 1. Okay, excuse me, can you mute yourself? Noise is coming. Thank you. Okay, so after all this arithmetic, we have arrived at the intensity of the diffraction pattern. Okay, now uh, something interesting you can see from here. So this intensity will be 0 only when beta is equal to integral of pi, right? Because then the sine is 0 and you get intensity 0. So, and what is beta? Beta is given by here. I mean, so just if you substitute that here, you get b sine theta equal to m lambda, where m is equal to plus minus 1, 2 and so on. Okay, so this is the condition for basically minima. Now you notice that this condition is opposite to what you get in the interference. Okay, so interference of two slits, you saw that this was the condition for maxima, but here this is the condition for minima. I mean, of course, the b here is not the distance between two slits, but the basically the length of the single slit itself. So it's not the same thing here, but yeah, just to not get confused. And here, from here, you can calculate the angle of these minima, which will be just sine inverse of m lambda by b. So yeah, one thing you can notice here is that since sine theta cannot be greater than 1, so m must be less than b by lambda. So if you calculate b by lambda, the nearest integer, nearest, so the maximum m that can be there is the nearest integer to b by lambda, basically. Okay, so yeah, it's an interesting thing to notice. And so that intensity pattern, if you want to draw it as a function of beta, it will look something like this. So you have the maxima at beta equal to 0, right, which is I naught that we have calculated here. And then you have minima at pi and minus pi. Okay, then again you will have some maxima, then at 2 pi you have minima, then again 3 pi and so on. It will go on and on. Similarly in this side also. Okay, minus 2 pi, minus 3 pi. Okay, so as you can notice here, this intensity is getting decreased as we go, I mean as we move towards higher beta value. That is understandable, right? From here, because you have beta square in the denominator, so as you move to, you know, high value of beta, intensity is decreasing, and it is decreasing by square of beta, so it is not a linear decrease, it's a quadratic dependence. Okay, is that fine? Okay, so what about maxima? So one maxima, we know that at beta equal to 0 there will be a maxima, but what about different these maxima points? Where will they lie? So that's not very straightforward from this formula. So we know that you guys have studied differentiation, right? So you know that for extrema points, if you have any equation, and you like if you have any any equation involving two variables, you can find the extremum points by differentiating one with other, right? So we have the equation of I as a function of beta, so we can differentiate it with respect to beta to get the maximum points of this I as a function of beta, right? So if you differentiate the above formula, basically this one, which is I naught sine square beta by beta square. So I naught is constant. Sine square beta, if you differentiate, you get 2 sine beta cos beta, and then you have to differentiate the so basically the numerator. So one by beta cube, and 2 will be multiplied, and this is this should be 0 for extrema points. Okay, if you solve this, you will get sine beta minus tan beta is equal to 0. Now this we have already seen that sine beta equal to 0 is the condition for minima, right? And this second one, which is beta equal to tan beta, this is the condition for basically your maxima. Okay, so how to solve this equation? So you can graphically you can see that, so you have tan functions, right? 0, pi, 2 pi, you have this y equal to tan beta, and then you can draw a straight line y equal to beta, right? And these intersection points will basically give you the they will give you the condition for maxima. Okay, so you can find the angle of maxima. So you can solve for beta, and those points will correspond to maxima. Okay, so yeah, just to recap this, is that fine? So that's all for the diffraction. I think I went too long with this, so there is one very small topic. I want to also discuss the two slit Fraunhofer diffraction. Should we discuss that, or should we go to solve some problems? What do you say?
Yeah, we can discuss that.
Okay. So then, okay, then let's discuss very briefly. Two slit Fraunhofer diffraction. Okay, so yeah. So similarly, like we had single slit, now we have two slit. Now you will ask, what is the difference between interference and two slit for Fraunhofer diffraction, right? That is a natural question that arises. So yeah, I mean they are basically same thing, and you can see that in some limits this two slit Fraunhofer diffraction will give you exact results of Young's double slit experiment. Okay, so they are not very different, but yeah, let's see what happens. So, and these two slits are separated by a distance d, like we had in the Young's double slit experiment, and the width of these single slits are b as earlier, and again you have these divisions a1, a2, and so on. So let's name the divisions on the above slit as a1, a2, and in the and in the below slit let's call them b1, b2. Okay, so you have the lens here. So like earlier, these will have some path length difference. So here your screen is there. So what will happen is, first they will have diffraction among themselves, and then they will interfere with the wavelets from the second slit basically. So there will be interference as well as diffraction. Okay, and from the equations you can see how it happens. So we have already calculated the resultant amplitude due to resultant electric field due to diffraction. So for the first slit, the resultant electric field will be basically the same that we derived, cos omega t minus beta. So the light is same for both, that's why omega is fixed. Okay, and resultant electric field due to the second slit will be cos omega minus beta. Now there should there be some phase difference here? Tell me.
Yes, sir.
Okay, so yeah, some phase difference will be there, right? Because this distance, basically this will be the phase difference, right? And so let's call it b1 prime. So what is b1 prime? It will be again d sine theta, right? If this is your theta, right? So this phase difference will be what? 2 pi by lambda d sine theta, correct? Okay, so this phase difference is not so basically this phase difference is for all the all the divisions, basically pair of divisions. So like between a1, b1, and then between a2, b2, they all have this phase difference. Okay. So earlier
Yes,
when
sir.
earlier
Because
yeah, yeah,
sir,
earlier. Mm-hmm.
like because corresponding A and B are having distance between them D.
Yeah, that is what I'm saying. So this distance is d, then this distance is also d, and so on. Okay. So earlier when we were studying the Young's double slit experiment, we did not take into account this secondary divisions of the slits. Okay. What we assumed is that the slit is uh, such that there is there are no secondary wavelets coming from the single slit. Okay. So that is the only difference here, is that now we are considering divisions of individual slits. Okay. So now these two, E1 and E2, are the resultant electric field due to slit 1 and slit 2, and now they will interfere. Okay. So interfere means they uh, they will just add up, right? So E equal to E1 plus E2. So sine beta by beta, you have cos omega t minus beta, and then you have cos omega t minus beta with a phase difference of phi. So this phi is bigger phi, capital phi or whatever. It is not the same phi as before. Okay. So this is again cos c plus cos d kind of formula. So you can just simply calculate it. So it will give you 2a sine beta by beta cos gamma. I'll tell you what gamma is. And then you have cos omega t minus half beta minus half phi. Okay. Here basically gamma is phi 1, phi by 2, not phi 1. There is no phi. Okay. So now you see the resultant electric field has this amplitude, okay, which is a multiplication of two different kind of two different uh, angles. One is beta, one is gamma. So yeah, and gamma is basically phi by 2, or in terms of d, we can write it as sine lambda pi by lambda d sine theta, right, from here. Now so the resultant intensity will be just the square of this amplitude, which is 4 I naught. So I naught is basically a square. Okay. So now you see this is just the intensity, due to the diffraction that we found, not the 4, the I naught. This was due to the diffraction that we got in earlier case also, and this 4 cos square delta is because of the interference. Okay. So let's call it equation 2 maybe. So the diffraction pattern, if you will plot it, it will look like something like this. So it will have a profile of diffraction like this. Okay. But inside this profile you will have this interference thing. You remember the interference pattern, right? Okay, so it will look like something like this. And you can now from here you can see that uh, yeah, from here you can see that if b is very small, so b is small means we don't we don't have to consider this division of wavefront. Then uh, this sine square beta by beta square basically will have no variation with theta, right? Because oops, sorry, what happened? Yeah, sorry. Uh, what is happening? Yeah, because what is what is beta? Beta is pi b sine theta by lambda, right? So basically sine beta
Yes, sir.
depends on theta, correct? And if your b is very small, here b is multiplied, so if it tends to 0, then beta will have basically it will be it will not have much variation, right? It will be almost constant. So this diffraction pattern will not appear and you will get only the interference. Okay, so you will have only the 4 cos square delta, which was the intensity due to the interference that we have already calculated during Young's double slit experiment. So what you will see in this case is that now you will have all of them equal like this. Understand? Yeah. So that's how you can understand how this two slit diffraction is. Basically, this is a general case of interference. So interference is a special case of this two slit Fraunhofer diffraction in this way. And similarly here you can get the minima condition. So when I equal to 0, I equal to 0 when when there will be beta equal to pi, 2 pi, 3 pi and so on. And this will give you the condition for minima b sine theta equal to m lambda. M will be your integers. So this is one condition, and I equal to 0 also when your lambda is equal to pi by 2, 3 pi by 2, 5 pi by 2, because cos is there, cos lambda is there. So this condition will also give you I equal to 0, and from here you get this condition. Okay. And we know that also from interference that maxima will happen when, so basically interference maxima, so these points, these all interference maxima, they will happen when y is equal to integral of pi, so 0 sorry, 0, pi, 2 pi, and so on, or when d sine theta equal to 0, lambda, 2 lambda, and so on. Okay. Now one interesting thing is there. So what happens when this is satisfied, and also b sine theta is equal to 2 lambda, 3 lambda. So what happens when these both things are satisfied? This can happen, right? So this is the condition for minima, as we see here, the diffraction minima, and this is the condition for interference maxima. So what happens when both the conditions are satisfied? Anyone? Hello.
Yes, sir.
So yeah, can you think about what happens?
So maybe there is dark thing.
Yeah. So yeah, basically what will happen is that, so suppose, this is the third order maxima, right, for interference. Okay, so that means b sine theta, if b sine theta is also 3 lambda, then at this place, so because the third order is maxima for interference, and this is the third order minima from diffraction, so these two will overlap basically, and this one will be missing from the diffraction pattern. So this we call missing order. Okay, so there will be a dark area, so it's called missing order. Okay, so this is something interesting that happens in the two slit Fraunhofer diffraction. So we will see some problems based on this later. Okay, so yeah, I think that that is all for two slit Fraunhofer diffraction. We also have the N slit and the diffraction grating, but I think that we can cover in the next session. So for now, let's move to some problems. Do you have any question till here?
No, sir.
Okay, thank you. So yeah, let's move to the first problem. Okay, so this is the easy one. So a plane wave of wavelength 500 nanometer falls normally on a long narrow slit of width 0.5 millimeter. So slit width is given. Okay, lambda is given. The angle of diffraction corresponding to first minima is. Okay, so yeah, first for the first minima is it's asking the angle of diffraction. Okay, how to calculate?
B sine theta is close to 10 lambda.
Yeah, we have this condition, right? And so sine theta will be basically, and first minima is m equal to 1, so just lambda by b. So 500 nanometer divided by 0.5 mm equal to just 10 to the power minus 3. So theta will be sine inverse of 10 to the power minus 3. I think it will be a very small number, very small angle. So yeah, you can calculate it. I think, yeah, so the answer is basically first one. This is easy one. Okay, so let's move to the next problem. Sorry. So here the question says a convex lens of focal length 20 centimeter. Okay, so there is a convex lens, focal length is 20 centimeter given, is placed after a slit width of 0.6 mm. So B is given 0.6 mm. Now if a plane wave of wavelength 600 nanometer, so lambda is 600 nanometer, falls normally on the slit, okay, parallel, the separation between the second minima on either side of the central maxima will be, okay. So here the screen, and you have central maxima, and then you have yeah, central maxima. This is the first minima, second minima, and then you have second minima. So basically we have to calculate this distance. Sorry, yeah, this distance, okay. How to calculate this? So again, for minima we have this, sorry, b sine theta equal to m lambda. This we have, right? And here m is 2, so sine theta is 2 lambda by b, right? So angle we know, but how to calculate this distance?
Trigonometry.
Yeah, we can.
The distance.
So this is the theta. Yeah, this is the theta. Okay. And so what is sine theta? So let's call this distance our x that we have to find. So sine theta is basically x by this distance. So as in the case of Young's double slit experiment, we assume that this distance is basically larger than, this d is larger, greater than d, that there we assumed, right? Here also we can assume this focal length is larger than b. So we can write sine theta as x by f. Okay, so x will be basically 2f lambda by b. Is this fine?
Sir, sine theta x by f.
Yeah, I mean sine theta basically should be x by this distance, but we are assuming, so let's call this hypotenuse h. So we are assuming h equal
yes sir,
similar to f, okay, because this distance is larger than the other distances in the system. So this b is, so you can see here, right, it is 20 centimeter the focal length, and the slit width is just 0.6 mm, so it is larger than. So we can make this assumption like we did in the Young's double slit experiment. Is this okay? Okay, yeah, so then you can just calculate it very easily. So 2 into to 20 centimeter is 0.2 meter into 6 into 10 to the power minus 7, because yeah, divided by 6.6 mm is 6 into 10 to the power minus 4. 6 goes on. 4 into 10 to the power minus 4 is equal to 0.04 centimeter. And I think it's asking the separation between the second either side. I think it should be twice of x, so both sides. So I think the answer should be D. Yeah, is that fine? Okay. So yeah, in this kind of problem we have to make these assumptions. Okay, now let's move to the third problem. So it is based on the previous problem. So it's asking what is the ratio of the intensity of principal maximum to the first maximum on either side of the principal maximum. So basically it is asking, so we have this principal maxima and then the secondary first maxima. Okay, so what is the ratio of this intensity? So this we know it is I naught, right? What is this? Any idea?
I naught by 27.
I naught by 27. How? So first you have to calculate the
Maybe 21.
beta corresponding to the this secondary maxima. Sorry, the first maxima. And how to do that? So using this transcendental equation, where from here you have to calculate it. So the first maxima, it happens if you solve this. I mean, you can do this using any graph calculator online or anywhere. So it happens at around beta equal to 1.43 pi. Okay. Oops. So that you have to put here. So then the intensity will be I will be I naught sine square 1.43 pi divided by beat by 2 no and 1.43 pi square. Okay, and yeah, this will be the intensity of this first minima, and intensity of the principal maxima we know it is just I naught. So it is just I naught divided by this. So I naught get cancelled. So 1 by this thing. So if you calculate it, it will be around 0.045, which is 22.2. So yeah, I think so yeah, 23 should be the correct option, I guess, because this 1.43 pi is not exact. It is close to 1.43 pi, so that's why you don't get the exact answer. But yeah, I think this is how you can calculate it. Is it fine? So you don't have to remember this. I don't think this kind of problem should be there in the exams, because then you have to solve this equation, which is not easy. Which one? Yeah, sorry. Yeah. So solving this is not, I mean, you cannot just intuitively solve this. You have to use some, either some graphical methods or some online tools, computational tools. So yeah, don't worry about this. It is just for, just demonstration purpose. Okay, let's go to the next problem. Yeah. Now this is based on the double slit diffraction that we just studied. So a double slit diffraction pattern is formed using mercury green light at 546.1 nanometer. So lambda is given 546.1 nanometer. Each slit has a width of 0.1 mm, so slit width is given. Now the pattern reveals that the fourth order interference maxima are missing from the pattern. Okay, so that's what I was saying. So fourth order interference maxima. So basically you had this profile, right? No, this if this is the fourth order interference maxima, this one is missing. Okay, this is the information given, and you have to find the slit separation, which is D. Okay, how do you solve it?
That one condition, sir.
Yeah.
D
So
sin theta.
yeah, we have these two conditions. This is for the interference maxima, right? And we have the diffraction minima, single slit diffraction minima condition given by this. So here let's call it n by n, doesn't matter. Okay. Now what we studied is an interference maxima of order m will be missing if it coincided with the diffraction minima. Okay, so I mean, if there exists this n such that d sine theta equal to m lambda and b sine theta equal to n lambda, so this happens simultaneously. Okay, so that means, so both these conditions are satisfied. So if you take the just divide them, you get d by b equal to m by n. Okay, so yeah, here m is given, b is given, d we have to find out, and n we have to find out. Okay, so first, how do we get which diffraction pattern is there, which diffraction minima is there at this point? How do we find it? That we have to find out, right?
Minima conditions of diffraction.
Sorry,
From that we can find.
which condition?
Sir, condition. D sin theta is close to m lambda.
Yeah, but yeah, but you don't know which order of this diffraction minima coincided with this this maxima of the interference pattern. So here there is a trick that we uses. Okay, so so we know that so this m by n, So this m by n should okay, yeah. So this m by n should be, simple rational number, right? And otherwise these two condition will not get satisfied. I mean, this will not uh, you know yeah, we know that n can be integers, n can be integer only. So n okay, so let's first take n equal to 1. Okay, what happens is, then you have d equal to 4b, which will be 0.4 millimeter. Okay, now you can also say that at n equal to, we can also take n equal to 2. Okay, so let's see what happens when you take n equal to 2. So then if you take n equal to 2, so d equal to 2b, it is 0.2 mm. Okay, yeah, but then this corresponds to m by n equal to 2.
Sir,
Yeah.
can we find it like you told us that m should be less than equal to b by lambda,
No, from
or
there.
it should be
No.
less than b by lambda.
Yeah, that is for the single slit
Okay.
diffraction pattern, but that we cannot apply here, because we have to find that m, that order which coincide with the diffraction minima. Okay, single slit diffraction minima. So basically, so
Okay.
this minima that is happening, which order of minima will coincide with the interference maxima, fourth order interference maxima. Okay, so yeah, so, I mean, very likely it should be the n equal to 1 first order, because uh, yeah, that I am trying to think about. There was a easy method to do this. Yeah, sorry. So m okay, so I was working out with logic. So n equal to 1, we get m by n equal to 4. If n equal to 2, we get m by n equal to 2. Okay, uh, okay. Hmm. Yeah, why not 2? 2 should also work. Because both options are there. No, yeah.
Sir, there should be use of lambda somewhere, I think.
Sorry.
Lambda,
Yeah, from lambda, I
there
mean,
should be
we can calculate theta from here. So n lambda by b sine inverse, we can calculate, we can basically we can calculate the angular position of the minima. That is fine as a function of n, right? But that complicates the things, because then we have to find the angular position from here for the interference pattern, which is sine inverse m lambda by d, and then you have to match them. This m we know it is given fourth order. No, this was not done like this. I remember this. There was a easy method to do this that I have forgot now. Okay, maybe we will revisit it next time. I'll have to check. This is complicated. You cannot match. You cannot calculate these angles and match it. There was a very simple logic to it. Okay, no problem. We can discuss it again. Do you have anything in mind?
Not as of now, sir.
Yeah, we can
We
discuss
can
it
discuss
again.
later.
Yeah, sure. Okay, so there is this problem which is based on the previous problem, which we can solve. So from problem 5, what is the irradiance or the intensity for the first three orders of interference fringes relative to the zeroth order maxima? Okay, zeroth order maximum is this the middle one, principal maximum, and then you have these things. So these first three fringes we have to find the relative intensity. Okay, so this is easy, right? We know the intensity. We have the intensity formula basically. I naught cos square, I think 4 I naught cos square delta gamma, and then we have beta by beta square, right? And so yeah, we can just also beta we know it's by b sine theta by lambda, and gamma is just phi by 2, which is pi d sine theta by lambda. Okay, and at the maxima we have phi equal to sorry, so m pi corresponds to the maxima, this one. Okay, so yeah, so this is same for all the this is same for all the interference pattern. So interference maxima. So the this variation will depends on the single slit diffraction part, which is given by, so basically maxima by so I mean order, so intensity of mth order by the maxima intensity, it will be governed by this term only, right? Because these all have m these all are at integral of pi distance, integral of pi at, I mean phase angle pi. So this is same for all. I mean cos gamma is same for all, right? But this modulation happens because of this single slit diffraction. Are you able to understand? Yeah, because we studied, right, in the normal interference pattern, all of them have the same intensity. Okay, so this difference in intensity comes due to the single slit diffraction term from here, which is this. So you have to just calculate this thing, and we know that beta is so beta beta we can find from here pi b m by lambda, sorry, pi b m by d, right? Because sine theta is equal to wait, B sine D. Sorry. Oh, okay, okay. Yeah, yeah, yeah. Wait. Yeah, yeah. So this is the beta that we can use, but uh, mm, no. Wait. B sine theta equal to m lambda. This is for minima due to the single slit, right? We cannot put it here. So first three order. Mm, I see. Okay, okay, yeah, yeah. So sorry. So okay, so till here it's fine, right? Till here it's fine, right? Now what are the values of beta for these interference maximas, right? So that we have to find. Now beta is what? Beta is pi b sine theta by lambda. Okay. Now for so this beta depends on this sine theta. Now what is the sine theta value for interference maximas? So that we get from here, right? Sine d sine theta equal to m lambda. This is the interference maxima condition. So from here we get the sine theta value and we can use this. Okay, so basically you have now sine m lambda d by m lambda d square. This is the relative intensity. So now for you can calculate this for I1. So just put m equal to 1 here and then m equal to 2 here and so on. You can find out. Is that okay? So the answer is I think this one. So you see the intensity gets decreased. So the first one is 80%, then you have 40%, then you have only 9% of the central maxima. Okay. Did you understand this?
Yes, sir.
Okay. So yeah, here just we have to see that this cos gamma will have no no change when you go to different orders of interference maxima. What will change is this sine beta by beta term, because this is what is modulating this intensity. Okay, this beta square which is there in the denominator, this is decreasing the intensity as we go to higher beta values. So that's why this relative intensity, you have to just take the ratio of cos square delta cancel out, 4 cancel out, I naught cancel out, only this remains. Okay. Okay, so I think that's all for today. It's late now, so we will we will discuss the n slit interference and diffraction grating next time. Okay, So yeah, I'll keep it. I mean, I'll cut the session till here today. Do you have any other question?
Sir,
Yeah.
sir, can you tell if there is any negative marks for the NPTEL exam?
Sorry, there is
Any negative marking for the NPTEL exam?
negative marking in NPTEL. Yeah, yeah. I think there is negative marking. Yeah.
Okay, sir.
Yeah. I think exam pattern you can check on the NPTEL website. Somewhere there should be information about it. Or when you register for the exam, you will get all those information. But as far as I remember, I think there is a negative marking. But I can check the detail and let you know in the next class. Okay.
Okay, sir.
Okay.
In the NPTEL website, such information was not given, sir. Only they told that options will be provided and it is a computer-based test.
Yeah, yeah, yeah. I know. So okay, okay. I'll check it and tell you. Okay.
Okay, sir. Okay, sir.
Oops. Sorry. Okay. Thank you for joining. Let's meet next. So next Saturday, instead of Saturday, we are meeting on Friday. Okay, because I have to travel on Saturday. So you will get the mail for that. So there is a slight change in schedule. So we will meet on Friday, 3 p.m. Okay. So sorry for any inconvenience. Okay. So just yeah, heads up. Thank you. Bye.
Bye, sir.